Okay, anyways, here's Green's theorem, and the way it was described to me was kind of like you have these farmers who want to figure out the area of their, I don't know, their fields. Maybe this is, and back in the feudal time or back in England or somewhere, they started having all these weird shapes. I don't know, it's just an issue with societies. Maybe it even extended back into Egypt where they're trying to figure out regions of lands and who owns what and that sort of thing. So these kind of problems are important. Um, Unfortunately, maybe it was hard to figure out the area of a region like this, and they figured one way to do it was just by walking around the region. There's a clever way you can figure out um, the area by walking around the perimeter. Okay? And that's how I kind of think of Green's theorem. Um, you could basically do a line integral around this, and it'll tell you the area inside of it. Okay, but in our case, in in modern times, the way we'll use Green theorem is kind of like a new method for doing a line integral of a vector field on some sort of curve, and we'll be able to go back and forth with it. Okay, so it's going to be able to convert your standard line integral m dx plus m dy. Okay, and this is our friendly line integral of the vector field along some curve C, but there's kind of some restrictions we have to follow with regards to the kind of region we're integrating around. So no longer is it just a single curve with two distinct endpoints. So these curves have to be closed. In other words, they begin and end at the same place. And there's some other restrictions involved too. Okay, so anyways, this is the differential form for the line integral of the vector field on some curve C. And we're going to say we can rewrite this as a double integral using this thing here, a difference of partial derivatives. Okay, so we'll be doing, and the vector field is always given mn, right? So we're going to take the derivative of this with respect to x and then minus the partial derivative of this with respect to y. Okay? And then we can integrate that over this region and we'll have the same answer as that line integral or vice versa, right? Depending on whatever you want to do. Okay, so first we need to kind of prove to you that this will work. And we have some restrictions to deal with. First off, the region we're working with doesn't necessarily have any, it doesn't have any holes in it at first. Later on, we'll see we can get around that. But we'll call the region R. The region R must be what they call simply connected. And we won't harp on this too much, but I'm sure if you took advanced math, maybe it'd be more, they would look into the nit and gritty of it. But well, what does it mean to be simply connected? It basically is a region like this. Okay, this is simply connected. Yes, simply connected, but something like this where it's two parts, this would be no. Okay, so other versions, you can't have a hole in it either. Okay, so no, that would be bad as well. These are not, this and this are not simply connected. Okay. On top of that, we need the line integral to be kind of nice. We need the line integral to be simple, or sorry, the curve C, the boundary of that region, it has to be simple. So it doesn't intersect itself, so none of this weird business. So that would mean it's not simple. We're also going to require m and n to have continuous first partial derivatives. So, there's these first three items have to be fulfilled. And then fourthly, we're going to require the region to be what's called horizontally and vertically simple. Okay. So if I can ever get these two pieces of paper apart, that would be great. All right, so so at the end of the day, our region that we're going to be working with will be something like this, where maybe we have two different curves. And that's what we mean by being horizontally or vertically simple, depending on the orientation that you're integrating with respect to. We want to be able to write the curve in two functions. So I would call this guy some function 1 of x, and this guy some other function 2 of x. Okay, so this would be good. Something like this would be bad, right? So I wouldn't have any weird loops or something where it's obviously not a function. Okay, so this bottom curve, I would have to split it into parts in order to, and you could probably do that, it wouldn't be a big deal, but we're just not going to bother with that. So no go on the second picture. Our pictures are mostly going to look like this, okay, which is nice. Okay, but once we get it into that version, we can now sort of do our proof on this form. So let's say I'm going from A to B here. And the proof, you could split it into two parts. And what you're going to do is kind of show that this thing is this thing, and then prove that this thing is this thing. Okay, so the first part of the proof, and we're just going to do part of it. We're not going to do both parts. I don't know if the book even has both parts, but I'm going to show that this thing right here is equivalent to this thing over here. Okay, with the double integral in front. So I'll start with this guy and proceed forward. Okay, so I want to show that the first part of the differential form of the line integral, which is m dx, sorry, and that should just be one integral there. I want to show that that thing is equal to the double integral of the negative of the partial of m with respect to y, I believe, dA. Okay. And in particular, I'm working with this region right here. Okay. Okie dokie. So let's work with the left-hand side. So I note this thing right here. And the curve I'm working with is a curve all the way around. So this would be like C1, this is C2, and the whole curve we could call C. So this is a curve C. But I'm splitting it into two parts, so C1 and then this is C2. Okay. So the integral around the whole curve is equal to the sum of the integrals around the parts. So this would be C1 m dx plus the integral around C2 of m dx. And then I can rewrite m, because right now it's a function of x and y. But I can rewrite it in terms of just x using these functions here. Okay. So normally m would be like m of x comma y, but now I'm going to rewrite it as the integral of m of x comma, and c1 is f1, so comma f1 of x dx. And then I can just integrate that from a to b. So it's kind of like I parameterized it in terms of x. Right? And then plus the integral from a to b of m of, and well, it's not exactly a to b, right? Because this other curve is going to go in the other direction. So it's actually going from b to a. So let me adjust that. It's going from b to a. Right? And then it's, in this case, x comma f2 of x dx. Okay, I could combine these into one integral by noting that the integral from b to a is just the negative of the integral from a to b, right? So I can rewrite this as m of x comma f1 of x dx minus the integral from a to b then of m of x comma f2 of x dx. And then I could rewrite all of that junk as one integral from a to b of m of x comma f1 of x minus m of x comma f2 of x dx. And we're almost there, right? What are we trying to show? We're trying to show this factoid with a double integral. So I kind of have now a double integral. Remember, you can rewrite a difference like that as the result of doing this other integral inside here, right? So if I just make this the partial of m with respect to y dy, and then I'll have dx out here, and then the bounds curve the curve, right? So it's going curve the curve and then point the point. This will be f1, or rather f2, and this upper guy will be f1, and then going from A to B. Okay. Or did I reverse those? It should go f1 to f2. Well, good enough, right? Why is it good enough? Well, what am I trying to do? I'm trying to show that that's equal to the negative of this, and that's kind of what I've done. So this integral over this region as it sits, what are the bounds on that integral? Well, I'm going from curve to curve, so f1 to f2, and then from point to point A to B. And if you make it negative, you can flip this inner integral and make it positive. Okay, so that's what this will become. If I flip the inner integral, this will just be equal to the negative double integral from A to B. And on the inside here, I have f1 to f2 of the partial of m with respect to y dy dx. Or in this case, I'll just put a big dA there. Okay? And that thing is this thing here, which is what we're trying to show in the first place. Okay, so I mean, you really need to have this simple form to make this pan out, and then it's going to come from kind of a parameterization in terms of x, and then taking advantage of our definition for the iterated integral in order to rewrite this single integral of a difference as a double integral, and that's it. Okay. Okay, so hopefully that kind of convinces you, and then you would have to do the other part, but let's not. And so you did. Okay, all right, so let's apply this and this next section in my notes. So we're going m dx plus n dy into our double integral, partial n with respect to x minus partial m with respect to y dA. Okay, so first, just line integrals in general, line integrals of vector fields, and then we'll talk about work, which is kind of the application for line integrals. The book wants you to evaluate this critter, y minus x dx plus 2x minus y dy. And maybe remind yourself that this part here is the m part, and this part here is the n part. Okay, we want to integrate in problem 7 over this boundary region, this curve C. And this curve C is the boundary of the region between y equals x and y equals x squared minus 2x. Sorry, I ran off the page there. All right, so this curve here, this y squared minus 2x, you get the intercepts, so x equals 0 and 2 if you factor it, so it equals 0. The vertex you can always find by getting taking the derivative and finding its extreme value, which will be the vertex, right? So it'd be 2x minus 2, or you just do the negative b over 2a thing, works as well. Okay, so this would be 2x is 2, x is 1, and then plug that back in. So 1 minus 2 is negative 1. So the vertex is 1, negative 1. Okay, so it's just a parabola. Let me draw it. So its intercepts at 0 and 2, and then we have its vertex at 1, negative 1, so it looks like this. And then the other line is the diagonal line, and we want to evaluate that line integral around this region here. Okay, but what Green's theorem is saying is instead we could just do a double integral of the partials of n and the difference of the partials of n and m. So first we have the partial of m with n with respect to x. So the partial of this guy with respect to x is 2, and then minus the partial of m, this guy, with respect to y. So that will just be 1, and then dA. And then I'll rewrite it in the traditional ordering. So 2 minus 1 is 1, and then I want to go dy dx. Okay, so the bottom curve, and my Riemann man is going like this. Okay, so the bottom curve is the parabola, x squared minus 2x, and then the top curve is just y equals x. And the Riemann man is obviously running from 0 to whatever point this is. Okay, so what the heck is that point? Well, you just set the two equations equal to each other. Okay, and then solve. So I have x squared minus 3x is 0. Factor out the x, you get x minus 3 is 0. So x is 0 and x is 3. So I'm going from 0 to 3. Okay, so it just gives you another method for evaluating a line integral. Maybe you don't know how to parameterize this curve in order to eliminate it, get the x's and y's and get it in terms of t's. You know, for whatever reason you need it, it's there. You know, we have this other method for evaluating line integrals. Okay. Well, also we use these for finding work of a vector field on a particle. So work. And the book on 23 wants to find the work done by this force field. 23, the force field is given as x to the 3/2 minus 3y, comma, 6x plus 5 square root of y. Right. And the curve I'm integrating over is a triangular region with endpoints at 5. So this point is 5, 0, and then 1, 2, 3, 4, 5, 0, 5. Okay, and we have to go in this order. If I didn't make that clear, you're always going in the counterclockwise direction around the region. Okay, so the Green's theorem, sometimes you'll see it written with a weird circle thing like this. And I think it's that way in our book, and it's telling you have to go in the counterclockwise direction around the region. Okay, so if I didn't make that clear, hopefully that's clear now. Okay. So anyways, we want to do this this guy. I want to do it with a double integral instead of a line integral. So we should be able to just kind of dump in the difference of the partials again. So the derivative of this guy with respect to x is easy, it's just 6. And then minus the derivative of that with respect to y is -3. And then we integrate over this region. So let's do the traditional ordering dy dx. So our Riemann man is running like this. And curve the curve, so curve to curve, going from y equals 0 to y equals, looks like slope -x, y-intercept is 5, so -x plus 5, and then the Riemann man is running from 0 to 5. Okay. And then you would have, I assume you know how to evaluate integrals by now, so I'm not going to bother. You could do that on your own. Okay. Okay. So there's that. Let's look at the other direction now, kind of going from double integrals to line integrals. So this would be more like you're the English farmer and you need to figure out the area of your field, and you can do that by kind of walking around its boundary and working with that. So we're going from the double integral now to the line integral. And the differential form is this. Okay, so we just look at some easy ones. Finding area. So area of a circle. Can you find the area of a circle doing a line integral? Is kind of the question. Maybe this would be a good question to bring up at a parlor, at a party, something like that. Assuming that you're friends with a bunch of math geeks, right? Don't bring this up around other people. They may not like you for it. Okay. Region bounded by the graph x squared plus y squared equals a squared. Okay. Okay, we could draw that region. It's just a circle with radius a. So this point here is at a comma 0. Okay, so the double integral isn't so bad for this, right? We could actually just do it with a double integral and then probably go the polar. And I mean, you could do it with geometry. So the radius is a, so its area is pi a squared. Okay, so I already know the answer, but that's not the point, right? The point is we can figure out the area by doing a line integral. Okay? So anyways, when you're figuring out area using a double integral, your integrand is just 1, right? And then you're going curve to curve, point to point, dA. The trick to this is kind of fabricating your parts. Okay, we need to kind of make up something for this part and then make up something for this part, right? And those somethings have to equal 1. And there's more than one way you could do it, right? You could say, well, let's let this equal 3/4 and let this equal negative 1/4. And then 3/4 plus 1/4 is 1. That will work. We want to standardize this so people don't go crazy trying to grade your papers. We always want to use the following translation. So we're going to let the partial of n with respect to x equal 1/2. And then the partial of m with respect to y equal negative 1/2. Okay, but there really is no unique way to do it. There's other ways. But this is the way you want to do it for us and the book. Okay, so once you have that established, then you can kind of finagle these parts by doing antiderivatives with respect to x and with respect to y. So n is the antiderivative of this guy with respect to y. So when you do that and we put it into this line integral, this thing will become y over 2. So it's basically just take the antiderivative with respect to y. Then if you do this part here, it's going to be, well, the antiderivative of m with respect to x. Okay, so what goes here, well, sorry, I'm screwing this up. What goes here is n. Okay, in order to get n, we have to go over here and work with this, and that part of it is right here. Okay, so it's like this part here, when I take its antiderivative, is giving me this thing. So I actually screwed that up. It needs a negative in front of it, right? Sorry. And then this part here, when you take its antiderivative with respect to x, is going to go right here. Okay, and the antiderivative of 1/2 with respect to x is just x over 2. Okay, and it should be ends up being plus. Okay, so let's see if I can piece that together again. So what's going on? I want to rewrite. Okay, so let's see, make it a little prettier, right? So I'm going from partial of n with respect to x minus partial of m with respect to y, dA. And what I'm saying is that this thing right here, as of now, is equal to 1/2 minus negative 1/2 dA, right? And I want to convert that into the line integral of m dx plus n dy, right? And the deal is this thing is going right here. Okay, so this thing is going to go right here, and I need to do its antiderivative with respect to x. Okay, if this is a partial with respect to x, in order to retrieve it, I need to do the integral basically with respect to x, and that's going to give me x over 2. Okay, and then the other part would be dy. So I just carry over this material, n dy. And then to get this part here, you're working with this thing, okay? And that will go then right here. And this thing is this guy right here, right? So that means this part, and I'm getting carried away with the arrows. Let me get rid of this arrow for consistency, right? I need to take then this part and integrate it with respect to this variable here, y. So if I integrate negative 1/2 with respect to y, I'll have negative y over 2, and then carry over the differential dx plus this x over 2 part. Okay, so hopefully that makes it a little bit more clear. It's kind of like a lot to stomach, but that's it. Okay. So you just have to be careful with your signs. Okay, and this will be d with respect to x. This will be with respect to y. Okay, so let me rewrite my integral so it's not looking so brutal. Okay, so my integral then, the curve integral is going from negative y over 2 dx to plus then x over 2 dy. Okay, now in order to integrate this thing, I need to do a parameterization of the circle up here. Okay, so sort of a standard parameterization of a circle, I use cosine and sine. In particular, I need to have a radius of a, so I'll use a cosine theta, or a cosine t in my case, comma a sine t. Okay, and I'll need dx and dy, right? So if x is equal to a cosine t, then dx is equal to negative a sine t. And if y is equal to a sine t, then dy will be equal to a cosine t. Okay, so I just need to go and take all this material and replace all of this. So it's an integral in terms of t. Okay, and on top of that, I should have noted that t is ranging from 0 to 2 pi. Okay, so let's go ahead and look at that. All right, so this will equal then the integral from 0 to 2 pi of negative y. So you just use a sine t. So negative a sine t all over 2 times dx, which is negative a sine t, dt. And we're going to be able to combine these into one integral. So I'm just going to go ahead and convert this part of it too. So plus x over 2, so a cosine t over 2, times dy, which will be a cosine t, dt. Okay, so I forgot my dt's over here. Okay, and this whole integral will go from 0 to 2 pi. All right, cleaning it up, and it does clean up well. What do we have? We have a squared sine squared t over 2 plus a squared cosine squared t all over 2. So you can factor out an a squared over 2, and you'll be left with sine squared plus cosine squared, which is just 1. Okay. I'm integrating with respect to t, so I can factor out the a squared over 2. Integral of 1 dt is just t. And then I evaluate that from 0 to 2 pi. And so what do I have? I have a squared over 2 times 2 pi minus 0, which is just 2 pi. And then that, what is that? Well, it's just pi a squared, which is the area of that circle. Okay, so it works. You can now figure out area just by doing a line integral on the boundary, right? Okay, so kind of, like I said, a neat parlor trick that you could impress all your math friends with, if you have any. And so on. So the last sort of Green's theorem thing, and maybe I should just note, this is theorem 15.9 in the book, doing this operation. Basically, if you have the, if you're trying to find area, you can do it by converting it to a line integral where the component's negative y over 2 dx plus x over 2 dy. Okay. Okay. So that was the differential form of the line integral of the vector field over the curve C. Okay. Right. So there's that. Okay. Lastly, and with regards to Green's theorem, and there's still one more section I kind of have to do, which is foreshadowing Stokes' theorem, the divergence theorem. But this is holy regions, regions with holes. It turns out that it's so long as the region is kind of really nice, like we don't have to worry too much about there being holes involved, and we kind of show you the logic involved here with that. Okay, so let's say I have a circle with radius 5. Okay, so we have this thing. I missed the point there. And then on the inside, we have another circle. Oh, it's not a circle, it's an ellipse, where the A value is 2 and the B value is 1. So remember, the A value is the distance on the major axis, and the B value is the distance on the minor axis. It's kind of like you have two separate radii, one radius in that direction, one radius in that direction. The longer radius is A, the shorter radius is B. Okay, so you know, you can have it as, you can parameterize it. First, the bigger circle, which I'm going to call C1, we can parameterize with the vector valued function 5 cosine t, comma 5 sine t. And then the little circle, I can parameterize using, so the 2 cosine t and then just 1 sine t. We'll sort of make that work. Okay, okay, so what's the trick? How do I do this holy region? You're going to kind of go around this circle for your first curve. Okay. So that will be your C1. And then you're going to go inside in this direction, and that would be your C2. And then you're going to go around this curve in the clockwise direction. Okay, so this curve we went counterclockwise. Now we're going to go clockwise. So I go like this in that direction. Then I go like this in this direction. We'll call that C3. And then I'm going to go back out of the inner circle in this direction, and that'll be C4. Okay. So again, I put it in a different color. I zip around like this, and then I go in like that, and then around the inner circle, and then back out. Okay, so why can I do that? It's because C2 and C4 are just negatives of each other, and they'll cancel out. Okay, so C2 will be the negative of C4, and the Pi had some theorem somewhere in the book that when you do this, those integrals will cancel each other, and basically you'll just end up with the line integral around this and around this. Okay? All right, and that's exactly what we want for our integrals. So the book wants you to integrate the given vector field with, I'll set it up. Okay, so it's this thing, e to the negative x squared over 2 minus y is the m component of the vector field, and then plus e to the negative y squared over 2 plus x is the n component. of the vector field. And you can see those would be kind of annoying to do. So let's convert it into a double integral. And even more awesome, when we convert it to the double integral, we need not really use integrals because we know how to find areas of circles and areas of ellipses. Okay? So anyways, converting it into a double integral over this region, and the region we want to work with is basically just this donut region. The double integral will be what? Well, again, it's a difference of partials, so I take the partial of this with respect to x and plop it here. So that's going to be 1, and then minus the partial of this with respect to y, which would be -1. In other words, I'll end up with 1 plus 1. And then we have dA. So this will be the double integral of 2 dA. And you can factor out the 2, and what is it? It's basically just the area of that donut. You can find the area of that donut using a well-known formulas from geometry. So the area of a circle is just pi r squared. So pi times the r, the radius of the circle we said was 5, minus the area of this ellipse on the inside, which maybe you don't know. Area of ellipse is just equal to pi times a times b. Okay, where a is that distance on the major axis and b is that distance on the minor axis. Okay, so this will be pi times a, which is 2, times b, which is 1. And so this will be 25 pi minus 2 pi, which will be 23 pi, then times 2 will give me 46 pi. Okay. So I didn't even have to do an integral on that guy. And you know, the original question was integrate this vector field over this curve, which is just a freaking nightmare, you know, but it turns out with a little geometry and Green's theorem, oh, it's simple. So they're trying to sell you on this idea that you know, you do the integral one way, it's easy. You do the integral the other way, it's hard. You have to know a lot about the integrals and kind of have a lot of experience in doing them. Probably with a computer, you could just do it always by brute force, but maybe not even then, right? I don't know. The integrals get intensely crazy enough. Okay, so anyways, the last section I want to look at are some alternative forms for Green's theorem.